Hello, welcome back. Let me remind you that we are discussing Brouwer equivariant degree. So let me just begin. Brouwer equivariant degree. Let's start. So, remind you that also that M will stand for all possible, put it like V, and I put here G, G. This is the collection of all admissible G pairs. So just explain it more clearly. What is M with G? This means this is the set of all F omega, such that here we have here A, this is V is equal. So V is a representation, an orthogonal representation of G. Omega is open, bounded, G invariant, and F from V to V is G equivariant, and CF is omega admissible. Okay, so this is the notation, and then of course the MG will stand for collections of all possible such admissible pairs. So now we can formulate the main results. This theorem will be proved, but not immediately. Let me write it down. This is basically saying the uniqueness, existence and uniqueness of Brouwer equivariant degree. So let's say it like this. So let G be a compact Lie group then there exists a unique function, and I call this function G-deg, that is defined on all admissible G pairs and with the values in the Bernstein ring of G, given by, and then we have here this G degree by, maybe write it down a little differently, given for F omega belonging to MG. Let's write it down like V by, and this will be written G degree of F on omega is equal, and this is the sum over, this is a finite sum, so we have to understand that this is notation that actually implies, because the element, this is supposed to be an element of the Bernstein rings, it must be finite sum. So this is phi 0 of G, and then we have here dH, that's the integer, and this integer depends on F of omega, and I move that's just simply indicate the product, this is just simply H. So this is H is the orbit type. Or in omega, this is an orbit type. Here, however, we just don't indicate it. I will show you that basically in this formula that summation is actually indeed over the orbit types in omega. That means it is those numbers. Wait a moment. It disappears. Those numbers D, H, F, omega, which are going to be proved are integers. Those numbers are all zeros for all the conjugacy classes H, which are not the orbit types in omega. So let me write it down. So this will be degree. This is a regular Brouwer degree, and now we take FH, restriction of F to the fixed point space H, and then you put here minus, and those are the let's say like this, K is strictly larger than H, and then we put here, this is dk F omega, so that's kind of a larger coefficient corresponding to the larger orbit type. Then we have here N H K, here we have the Weil group K, and everything is divided by WH, means the order of the Weil group of H. So that's first part, which satisfies the following properties. So we have here the properties called as P1, just property 1, and this will be additivity. And here we will assume that F omega is belonging to, this is belonging to M, and here we have here F minus 1 of 0 intersection omega is contained in omega 1 union omega 2, which are two open invariant sets which are actually contained in omega. So here we have here, those are also open sets, and of course they are disjoint. They are disjoint. So we have a situation in which this is our omega, and then we have here omega 1, omega 2, and the zeros are either here, those are the zeros, or those are zeros. There are no other zeros. So omega 1, and this is 1, this one is 2. So that's the situation. So in such a case, we have this so-called additivity property. That means the G degree of F on omega is equal G degree of F on omega 1 plus G degree on F on omega 2. And we have the next property P2, and this is called the homotopy property. And simply, if I put it like this, maybe I put it like this, F, which is defined from 0, 1 times V to V, is an omega admissible homotopy such that it means continuous, definitely such that for every t belonging to 0, 1, if I write it down, maybe 1, if I write f of t in the bottom by the definition is this f t, and this one is then, we have here that this f t and omega belongs to the mg, so up g on v, so that simply means in particular that omega is open bounded invariant G invariant set, and f of course is equivariant with t fixed for every t fixed t is equivariant. Then we have here the g degree, and here is f t omega is constant with respect to t, that means doesn't change. So this is called the homotopy. Then we have P3 property, P3, and it corresponds to the Brouwer degree normalization, so we will call it also normalization. And here, if 0 belongs to omega, which is contained in V, so this is open bounded G invariant set, so in other words, it's simply you can say that identity operator omega belongs to M. Then we have and the property is G degree, exactly for this pair, identity omega is equal the unit element in the Bernstein ring G. Just remember when we were talking about the Brouwer degree, this was 1. Degree was equal 1. 1 is the unit element in the ring Z of integer numbers. Now we replace the ring Z with the Bernstein ring, and that's the unit element. That's the unit element. And we add maybe this one, P4 property, and this is called the product property, product. And in this product property, we have like this. If you have here F1 omega 1, comma, F2 omega 2 are admissible G pairs, then we have that G degree of F1 times Cartesian product F2, and this is the Cartesian product, and this will be equal G degree of F1 omega 1 times, and this is a multiplication in the Bernstein ring AG, and this will be second one, degree of F2 omega 2, and that's the product. This is in A of G, AG. So this is product in A of G. So that's the property. So, and I will be proving all these statements, namely the first statement that we will need to prove, and it's not done, that this number is in integer. So we need to prove that this is integer. And then I will also prove that we have the product property, but I will do it not now, I will do it later, because in order to present formal proofs, we will need additional information, additional construction done, and this will take some time. So it is maybe a good idea to familiarize ourselves with the concept of the equivariant degree and do a few examples, show few more properties, and later, when we already have kind of a feeling about this degree, we'll try to present the formal proof of all these statements. So we will postpone most of the proofs for later, but since it is possible to use the definition here, which is presented in the form of the recurrence formula as the kind of a, let's say, initial let's say, like our definition given by this recurrence formula, which is based on the Brouwer degree, it is possible to prove some properties immediately just from the properties of the Brouwer degree. And namely, let me do the proof, and we will show that for example, the three first properties are satisfied. We will prove that P1 and P2 and P3. So let me maybe point out couple of things. So first remark. This is what I mentioned. One can prove that the recurrence formula that in the recurrence formula, so let's go and give a number to this recurrence formula. So this will be the number 1, in the recurrence formula number 1, all the coefficients D, H, F, omega, not nice, F, omega, are 0 for those conjugacy classes which are not, for all, which are not the orbit types in omega. So that's kind of everything. So let me recall how actually this formula is applied in order to give the definition. So namely, we go to this formula and we begin with H being the maximal orbit type in omega. So in such a case, since this is maximal orbit type in omega, so then you can see that this portion here, there are no k's which are larger than H in omega. That means this is the beginning of the recurrence. So you start with all possible maximal orbit types. There may be many of them. They may be one, maybe many. That's not important. And then once you compute for the maximal orbit types, you go down in the lattice and you compute the formula for the sub-maximal orbit types in omega. And then basically that's how it works. But in our remark, I claim that it is not important if K is here an orbit type, because if H is an orbit type, basically what I say is that in the case H is not an orbit type, that number will be always 0. And this is maybe a good moment to present a kind of a short, let's say, justification of this claim. Short justification of this claim. Maybe let's put it like that. I underline and put here indeed. So first observation is observe that if X belongs to V is such that G of X is equal to H. So that means that the point X has the orbit type H conjugacy class. So is such that then, and if we have here, no, maybe let's change it. I want to have it maybe differently. Not H. I put here K and H is a subgroup of K with the property such that with such satisfying and is satisfying, maybe satisfying that VH is equal to VK. So that means simply H cannot be orbit type. H cannot be orbit type because you see the fixed point spaces are equal. So that means that's exactly is the claim. So that means simply H is not an orbit type in V. Then what I want to show is basically that this number NHK must be in such a case equals 1. Indeed. Let's do it. Indeed. I will use blue for this little proof. I will use blue. So, okay. So, if this is not equal 1, then is if for contradiction it is not equal 1, so that means NHK is actually larger than 1, then of course capital NHK is containing, but it is not equal to the normalizer of K. So, in our case, there exists a G belonging to NHK satisfying the property that Gx is not belonging to VK. Because we have the property that if Gx belongs to Vk, for this particular situation, if and only if G belongs to normalizer. But we are taking that one, which is not in the normalizer. That means it's not in the normalizer of K, so it cannot belong to this particular space. It cannot be to this space. But on the other hand, what does it mean? G belongs to the NHK is meaning from the definition, let's write it down. G minus 1 subgroup of K, which is equivalent H smaller equal than G minus 1 K G, which is equal K prime. And we know in this case K prime is not equal to K. So what do I have here? Since H is smaller than K prime, so we have here that Vk, so put it like this, Vh is contains Vk prime. But on the other hand, we know that this is equal to Vk. So what do I get here? That Vk contains Vk prime. But that one is impossible. That one is impossible because because g of f does not belong to k, so this implies contradiction. That implies contradiction. They must be equal, but they are not. You see, that one is not belonging here. This belongs to vk prime. Okay? This vk prime. So we got it. So this is the statement. So how to prove that this formula, the recurrence formula, does not, let's say, has the coefficients. So let's return to the proof and let's try to show it, let's say, shortly. So first of all, we start with the maximal orbit type and then suppose that H is the first conjugacy class, in the lattice of conjugacy classes which occurs after the orbit types in V. So, what does it mean? That means simply that we have here K, that's an orbit type, so this is orbit type. And then we have here, K is larger strictly than H, and we assume that H is not an orbit type. So if it's not an orbit type, that means for certain orbit type K larger than that one, we must have that Vk actually is equal to Vh. That means there is no increase of the fixed point space. So what do we have in such a case? So we go to the recurrence formula and maybe look at this one. So first of all, we have here that then the degree of fh omega h is equal to the degree. That's a Brouwer. This is the same space. This is the same map. Must be equal. And from recurrence formula 1, we also have that this one. So let's write it down. Degree, I put it like this, degree fh omega. So this one is equal to the degree fk omega k. And this one is equal. So let's look at the formula. Where is formula? Oh, here. So let's multiply everything by WH. So in our case, this was our K. We take the K moment. So let's write it down. And that one is equal. So let me write it down. This will be like a D. I just simply write dk for simplicity. So this will be dk. Forget f omega times, and this will be wk. And then we have here plus, and then we have here k tilde, which is larger than k. and then we have here dk tilde times n, and this will be k tilde, and this is let's say number of elements in this formula. I got that this is this one. But then I look here. We just showed in particular that actually this one is also equal dk, and I can put here n hk because we notice this one is equal to 1. So I put here wk plus that one is equal k tilde larger than k, and this is dk tilde times n k tilde wk tilde. And it is now easy to remark that basically this is the same as to write, this is the set of all k tilde larger than, not k, but I write here h, because we have here additional one that we can add to this summation. So this is this term, put it here, and we can write it down. So this will be again dk, so it will be one more, and this will be nh, k, H, this will be the same thing, H, K tilde, W, K tilde. Should be proved. So maybe leave it as an exercise. In such a case, this will be also equal to K tilde. So, problem. We can put it problem. In any case, this statement will be again proved in a different way. Just simply wanted to emphasize something. So actually, if we add it here, so what do I have here? Maybe it is needed to add to our statement. Then this one is and if k smaller than k tilde, then n h k tilde is equal to n k tilde. So we should add that one. Okay, let's see if we can do it later. So this is a kind of a challenge. We'll try it. Anyway, we'll see. So of course, if you look at the statement that we have here, you have that part, and you have here the beginning of that one, which is this one. So this immediately implies that dh is equal to 0. So that's basically the idea. This is the idea of proof. And this shows you that there are certain properties of the numbers NHK, which has to be considered in this particular proof. We will be doing this particular, let's say, this proof will be done later, but since we will be using the recurrence formula for the computations, it will be kind of important to neglect all the non-orbit types in omega for the computations. This will save the time and allows us to compute the degrees directly, effectively, explicitly, without making too many unnecessary computations. So let's return to the proof, and mainly let's look into the properties. So here we have the property P1. Let's discuss the properties of proof of P1, and let's see if the property P1 is true. So namely, maybe let's say like this, write it down like this. Proof of P1 till P3, and notice, maybe P2 first. Notice that it is sufficient to show that this particular number DLF omega satisfies P1 and P2, namely, in this P1 simply means that you have here, this is DH, so that means simply that DHF omega is equal to DHF omega 1 plus DHF omega 2, and P2 is equal to DHF of T omega is constant. It's constant. So we can show, we show P1 and P2, so call this one like a number 2 and number 3. We show number 2 and 3 by induction over the orbit types. By induction over the orbit types. Namely, if you put here, if you assume first, if for maximal orbit type H in omega, we have that DLF omega is equal to degree of FH, and that one is omega H. There are there is no minuses. This part doesn't exist because there are no larger than H orbit types. So we can remove it, divided by WH. And in such a case, you can see that this is the regular, this one is the regular Brouwer degree. So we are getting, this is the same as degree of H, omega 1H, plus degree FH, omega 2H, divided by WH, divided by WH, and that simply is nothing else than, this is the H, DH of F omega 1 plus DH F omega 2. So the additivity is satisfied. Similarly, for maximal orbit type, you also get that this one is equal Ft for, this is for P1, and for P2, you can see that this will be omega, which is equal degree, and this is FHT omega, and again, here we have here WH, by the properties of the Brouwer degree must be constant. So we got it. So this is clearly satisfied. So now, so we can assume for induction, that the properties P1 and P2 are satisfied, for, let's say, so how we should do it? We should write probably how to write it? H or K? Okay, for H such that K is larger than H. No, so this is K. For all K such that, and here of course that one belongs to the phi 0 of G, so this would imply that K is also phi 0 of G. Yeah, so this is this one. This is assumption. So for K is satisfied. So this one. For this case, we have the formula. This formula satisfies the additivity property and homotopy property. So what do I have here? So what do I have here? We just write the formula and check it out. So what do I have here? So in such a case, we have here that for P1, it will be dH f omega, it is equal, and I have here degree of fh on omega h minus, and this will be, yes, and this is over k larger than h, and then we have here degree k f omega, and this is n h k w k w k tilde, no, w k, that's correct, and then we have here divided by w h, and then we have here additivity, so I can split degree, because this is Brouwer degree, this part has additivity property. So I can split these two things. I put it like this. This is degree of fh omega 1h. Very good. And then, since I will not fit everything here, so I put it again, degree of fh, and this will be omega 2h. And then plus, and what do I have here? I replace by the induction assumption, that one will be equal to the degree k, and this will be f omega 1 plus degree k f omega 2. See? Omega 2. So I can replace it, and then I get a sum. So first one goes to the first line, and the second one goes to the second line. So I'm getting here that this one is equal to sum. This is k larger than h. And then I'm having here d k f omega 1. And then I n h k w k divided, everything is divided by w h. Plus, and similarly in the second one, this will be the same, k larger than h, dkf omega 2, and this is nh k wk, and this is again divided by wh, and it is clearly that this is dhf omega 1 plus dhf omega 2. Now, I don't think there is a need to prove the homotopy, because you can see that this would be exactly in the same spirit of the recurrence formula. That means there is no need to do this proof again. As you rewriting this formula so many times, it makes us a kind of it's not really smart. It's not really smart. So we have it. So this is how it is. So now let's compute let's prove the formula 3. So this is P3. I need to prove formula P3. So what do I have here? So what do I have? I need to prove that G, I have to compute G degree of the identity, and this will be omega is equal to, and now what do I have here? I have here, this is again, by the definition, this is an element of the Bernstein ring, and it has the, put it like this, dH coefficients times the orbit times h. So in such a case, we know exactly what to compute. We start with the maximal orbit type. Since 0 belongs to omega, so maximal orbit type in omega is exactly G. So in such a case, what do I get here? So in such a case, I'm having here that dG will be equal, so this is equal, write it down, while group of G, clearly it is 1, and then we have here degree of identity on omega G. So you can see here that omega G and contains 0, so this is identity. So we have here that 0 belongs to, so put it clearly, 0 belongs to the omega G. So by the normalization property of the Brouwer degree, I'm obtaining this is 1 over 1, so this is equal to 1. Good. So now take any H which is strictly smaller than G. So that's an orbit type in omega, and let's compute it. So let's write it down. So what do I get here? So by induction again, we can do it by induction. So let's start with the first one like that, and what do I get here? I'm getting here that dH will be equal degree, and I have here identity, and this will be omega H, and this one is minus, and this will be sum, and this is K larger than H, and this will be dK and H, and HK, and this is WK. So if I start with the first one, so for example, take the first one after H, so this is the formula that we are using. So if I start with the first, so so we do it, yes, by induction, so I put it like this, by induction. So if this is the first one, so what do I get? I'm getting dH is equal. That value here is always 1 by the normalization, so I'm getting 1, and this is minus. And here, because there is no others, I have here dG, and this is N, and this is HG, and this is W of G, divided by W of H. So notice this was equal to 1, this is always 1, this was always 1, so I'm getting 0. So now we can assume that we have here for induction, so dH is equal to 0 for certain H smaller than G, and you can apply the recurrence formula here by taking another one, so put it like this, H for all, maybe put it like this, K, so it will be clear, K, for K smaller than it, so you can take the K larger than H, so you take the next one, and in the lattice of the isotropies, and you will find out that values except dG are equal, which is equal to 1, all of them are equal to 0, so That means everything will disappear except exactly the same sequence, 1 minus 1, which gives you 0. So that value is always 0. dH is always 0 for h smaller than g. So by induction or directly. So the product property we prove when we know more about the let's say about the certain regular approximations of the equivariant maps. Yes. Examples. Let's do a couple of examples. This is actually appropriate. Example. Maybe switch the paper. Examples. So we start first with the example of the group G, and I take this will be group O2 as we considered, and we take the representation. This representation is a reducible representation, two-dimensional natural representation of O2, so we can identify R2 with C. So in such a case, G, which can be written in our case as SO2, so those are the rotations, and O2 times kappa, SO2 times kappa, so those are the rotations. So it means simply that it can be considered as identified with the complex number, for example, gamma equals EI theta, and those are gamma times kappa, and now gamma acts on the complex number Z, so Z belongs to here, so this is Z, by simply complex multiplication, and kappa acts on the complex number just simply by conjugation. So in such a case, we have here a representation of O2, and one can now look at the picture. So what do I have here? This is my plane, and here we have here 0, and 0 of course has the orbit type O2, and then you take any point, and the orbit of any point is the circle. So just by rotations you obtained a circle, so this will be my G of the X. So this is my X, and here for real numbers that you are getting that Gx is simply equal D1, which means simply 1 and kappa. So 1 is just a rotation by trivial rotation, by multiplication by 1, and kappa is conjugation. You can easily notice it. So that means this is there are only two orbit types in this space, namely you can write it down, this is O2, and then we have the second one, this is D1. And we will take as a map, so take the map F that goes from V to V, and this map will have the following definition. This will be just simply minus Z, and we will come back to the linear maps of between two representations in a moment, in the next lecture actually, and in the next lecture we also find a general formula how to compute the degree for linear maps. And after that, when we'll have several examples applied, we will go to the proofs. So let's compute this one. What is the degree of it? So we want to compute what is the O2 degree of this map F, which is minus identity. So F, write it simply minus identity, and omega, put here omega is just equals unit ball in V. This is unit ball in V, so I put here omega, unit ball. So what is this degree equal? So the degree is equal X, and I put here O2, this is one orbit type, and the second one plus Y, and this will be D1. So let's start the computation. As you see, in order to apply the recurrence formula, this is my lattice of orbit types, so this is maximal. So I start with O2, which is in this case X. So my x is equal, and accordingly to the definition, this will be degree, and this will be f. And g, my g is O2, so I've just put here g, and that one is g divided by w of g. And we already know what it is, because we had this like in the minute ago. What do I have here? I have here that omega g, so g is equal to 0. So that's in the zero-dimensional space, 0 is an open set, so this open set has no boundary, so this is admissible, and minus, and there is only one map from 0 to 0, that's one that has a solution, so by the properties of the Brouwer degree, even without using anything else except the axioms, you are getting this is 1, and this one is, of course, Weil group is 1, so I'm getting here 1. So I'm getting the first coefficient. This first coefficient, I'm getting here, this is O2. So this is equal to 1. So I have to compute y, which will be equal, and let me do it like this. So this will be degree, and this is f. And my h now h is equal to d1. So this is my d1, so I put here h. And what I'm getting here, this will be omega h divided by, and here I'm having the Weil group of h. Okay, so what do we see here? So h is this one. So what is the VH? That means it is equal V d1. As you see from the picture, it is clear. dv1 is exactly the real axis. So this is real axis. So this is equal real axis. So this is one-dimensional space. So I can write it down that this y is equal degree of minus identity on the unit ball in R. So this is the unit ball in R, so the one-dimensional space. And this is divided, and Weil group, what is the normalizer of dy? This is actually d2, so the Weil group of d1 is equal to, let's say, z2, so the number of elements is 2, so I can put here 2. But that's not finished. So that's the first part. But here we also have minus, because it's x, so there has to be taken like this. So we have to take x, then you have to take n, h, g, and then Weil group of g. So what do I get here? I'm getting here, this is minus. We computed x was 1, so that value is equal to 1. This value is clearly 1. This value is also clearly 1. So I'm getting here 1. So now we go to the next one. What is the degree of minus 1 on R? So it is clearly minus 1 divided by 2, which is equal minus 1. And our G degree, which means in our case O2 degree of minus identity on the on the unit ball in this representation, we obtain this is equal O2 minus, and this will be D1. So this is O2 minus D1. So that's my first example. Let's do example number 2. So this is my B, and in this case I consider similar space. In our case it is, again, this is R2, and this one is equal to C, but the group is different. I take this group which is equal D4. Notice that this is contained in O2, so in such a case I can use the previous picture to identify the necessary properties. So my picture, so the action is given in the previous example, because as you see, D4 is a subset of, is a subgroup of O2. So we have here the picture. So maybe let me take here the, remember what is d4. d4 is a symmetry of a regular, of a regular fourgon, which means a square. I make the square in this position. So this is my square. So this is 1, this is I, this is minus I, and this is minus 1. And then we have here the following orbit types. So here the orbit types are d4. So 0 is definitely d4. So now on the black axis, I have here, as it is said, d1. So what is d1? So write it down, d1 as it is before, 1 kappa. 1 kappa. And we have also additional isotropies. And in this case, we have this isotropies. So this will be d1 tilde. So what is d1 tilde? d1 tilde is equal 1I kappa. So, and everything else, so 1 second, and that one is d1, put it like this, this is d1, this is black, and maybe the rest, the points outside is z1. So those are the fixed point subspaces in the V, and we can make a picture, let's say the lattice of isotropies. So we have here like this, this is equal to d4, stands here, and then again I have here d1, I have here d1 tilde, write it down, and now in the bottom I have here z1. So notice here that the dimension of the fixed point space, so this is 0-dimensional VH, so this is VD4. That one is 1-dimensional, and this is VH for H equal D1, so H is equal D1 or D1 tilde. And here the fixed point space is 2-dimensional. You see, 2-dimensional, everything, you know, like it fills the plane. So everything what is equal, and so the isotropy is equal to Z1 or larger, so that means the whole space. So this will be 2-dimensional. So this is 2-dimensional, and VZ1 is just simply equal to V. So in such a case, by applying, let's say, the definition of the equivariant degree, I will compute the same degree as before. So this time, actually, I'm computing D4 degree, and this will be minus identity on the unit ball, maybe I don't write it, just unit ball in V like that. And I know that this has to be as before. This will be, like, let's put it like this. X, and it will be like a little too many, so the X of D4 plus Y of D1 plus Z of D1 tilde, and this will be plus U of Z1. So we have 4 coefficients to compute. Let's do not waste the time, let's compute them. So we start with X, so we start with maximal. So in our case, the X is equal, so what I have here, I have the Weil group of D4. So remember, this is the whole group, our G is equal to D4. So the Weil group always one element. This is a trivial, so that means I have here the degree, and this is equal to F minus identity, F on G, and this is omega of G. So we already know that this will be 0 space, and this will be one element. 0 is mapped on itself, so the Brouwer degree is equal to 1. So this is 1 to 1, and we are getting 1. So the first coefficient, X, is equal to 1. Done. We go now, and we will compute Y. So in this case, let's write what is Y. and in order to compute it, because this is D1, so while group of D1, and then we have here degree of fh on omega h. This is one-dimensional subspace, so omega is an open set, open neighborhood of 0 in one-dimensional subspace, and then we have to take the x out. Then I have to take here n, and this will be hg, because this is the next coefficient, and then I have a while group of g. So you look here and you see this one must be equal to 1 because there is only one group G containing H, and this one we show this is actually 1, and we computed X which was equal to 1, and the degree of minus identity, in this case this is one-dimensional, so it will be degree of minus 1, so this is minus 1. Determinant of minus 1 is minus 1, so this will be minus 1. So what is the normalizer? What is the normalizer of D1? You can verify it. In our case, it's just D2. So we are having here, so D2, so we are having here the following number. So this is minus 1, this is minus 1, and this is 2. And we are getting this is minus 2 divided by 2 equals minus 1. Similarly, let's write it down. We don't need to be lazy. We are getting here, this is again the same formula like above, except the h, now h is equal d1 tilde, so we have again the normalizer of h is equal, so the normalizer of d1 tilde is again equal to d2. So I have here the following numbers. So this is again minus 1, this will be minus 1, and the while group of d1 tilde is again equal to, so this will be, equal to, so this will be 2, and we are getting here, this is again equal minus 1. So let's go and compute the number u. So u corresponds to 1, so this will, in this case, this will be degree, and we have here that fh is equal to f, and omega h is equal to omega. So you have to write it down. This is degree of f on omega. So this is minus identity on two-dimensional subspace. And then we have here x, because that's the previously computed, you see this is previously computed. You see there are three. So this is previously computed coefficient. So you have this, you have that. So maybe let's go also write it down. This is equal to minus 1. This one is equal to minus 1. So now we need to compute u, and we'll be using, you see, these three coefficients are correspond to the orbit types which are strictly larger than z1, so they have to be counted. So this will be again x times, write it down, n, and this will be z1g, and this will be g, w1g, and then it's minus y, and this will be n, and this is d1, and that one will be, z1, and this will be d1, w d1, and there will be additional minus z, and then you have here, I'm not able to fit it here, so I write it maybe here, minus, and this will be z, and this will be n, z1 d1 tilde, w d1 tilde. So let's write the numbers. So first one is 1, second one is 1, third one is 1. This one is minus 1 to the power 2, so this is 1. So of course everything is divided by the while group of z1. So now what do I have here? I have here this one is equal to minus 1. So what is the number z1 in d1? This is the number of the conjugacy elements to, let's say, conjugate. How many elements contains the conjugacy class of d1? 2. So this number is 2. And that one is equal also 2. So this is again minus 1, this one is 2, and this one is 2. And while group is actually, whole group is D8, so this is D8, so this is 8 elements. So we now can go and rewrite the formula. So I'm getting this is equal 1, minus 1, minus and minus, minus, and this minus gives you plus. So I'm getting plus, and this is 2 times, so I write it down, maybe write it correctly, minus, minus 1, 2 times 2, minus, minus 1, 2 times 2, divided by 8, and this 2 cancel, and I'm getting this is 4 plus 4 divided by 8 is equal to 1, and we can say we computed the equivariant degree of, put it like this, I put it in red, D4 degree of minus identity on these representations that I indicated. So we got this is equal. So what do I get? I'm getting this is D4 minus D1 minus D1 tilde, and this is plus Z1, and we computed the degree, equivariant degrees. You see, as you see, actually, this computation can be actually done by hands. By hands, it requires some knowledge about the representations, about the fixed point spaces, about the subgroups, their conjugacy classes, and NLH numbers, etc. As we will indicate in, let's say, using the additional examples, many computations can be done on the computers. Sometimes you can actually carry out the computations in such a case that it will be totally impossible to do it by hands, but still the method of the computing this recurrence formula is effectively giving us the formula for all these types of the degrees. So what is our next topic, next objective? Our next objective actually is to talk. Now, the next objective is to talk about the linear maps. So we need to develop a computational formula for equivariant, G-equivariant isomorphisms. Namely, let me point out what do I mean by this. Namely, I mean the following. So for a given G representation, orthogonal maybe, orthogonal G representation V and a linear G-equivariant isomorphism A from V to V, compute G degree of A on the unit ball in V, where V is equal to the set of all x's in V such that the norm of x is smaller than 1. So that's an open unit ball. So we want to compute this degree. We want to show how this degree can be effectively computed. So we will indicate that this degree can be computed fully using the spectral equivariant spectral properties of the operator A. So this is the end for now. In the next lecture we will derive this formula. Thank you.